start again. So just to reiterate, we have prime and maximal ideals. R a commutative ring. A is a proper ideal. That means it's a sub Rng, which is closed under multiplication from the whole ring, that Uber closure we talked about. And then we introduced, we looked at the ideal. We saw that for an ideal, you can look at the set of cosets, the so-called factor ring. It is itself a commutative ring with identity, right? So, and I'll just, just a reminder. We saw that R mod A, not mod A, R, this is a set of cosets, right? This is X plus A such that, X is in R. These are the set of additive cosets. That this is itself a ring with respect to the natural operations where you add representatives and you multiply representatives, like, X plus A times Y plus A is XY plus A, right? So, among other things, 0 plus A is equal to A. This is the 0 in this, right? If you add 0 plus A to anything, you get the same thing back again. And this is not from the multiplication. This is from the addition rule. The addition is very silly. Although it's no more silly than the multiplication, it says you add representatives, right? Like that. But anyway, a multiplication, the multiplicative identity serves as the, this is the multiplicative identity in R by A. Okay, so we'll need to remember those for proofs you look at today. That's why I'm reminding you guys. But anyway, the larger point was, since A is an ideal, we prove that those operations are well defined, and if we get a new ring called the factor ring, all right? And then, at the end of last class, I introduced the concept of a prime ideal and a maximal ideal, all right? It's a prime ideal if whenever you pick a pair of elements in the ring such that they're products in the ideal, well, that implies either one of them or the other of them, or both, is, again, in the ideal. This is just like prime factors work for, prime factorization of an integer. Maximal ideal is what it sounds like. It's the largest ideal that fits inside R, essentially. If you have another ideal which is between the maximal ideal and the whole ring, well, that other ideal, which I've used B to denote, it's either the ideal that we're talking about, A, or it's the whole thing. This is maximality. I claim that, so this is example 4.34, which I'm tempted to skip, but I will not because I think it's healthy for us to go through. This one's a little bit hard. My claim is that x squared plus 1, right? Remember what this means. X squared plus 1 times what? Times f of x, such that f of x is a real polynomial. All right, my claim is that this principal ideal generated by x squared plus 1 is maximal in the polynomials with real coefficients. All right, that's my claim. All right, so suppose that we have x squared plus 1 is a subset of, let's say, B. I'm changing my notation. My notes, unfortunately, uses A instead of B here, which I think is a very unfortunate sort of notational snafu. Anyway, so suppose that, right? And we'll assume that, x squared plus 1 is not equal to B, right? All right? So what does that mean? That means that there exists f of x in B such that what? F of x is not an element in x squared plus 1, right? So by the division algorithm, we have f of x is equal to q of x times x squared plus 1, right? But that's not it. If that were the case, if it were just that, if I look at the division algorithm of, f of x divided by x squared plus 1, if it was just that, if the remainder was 0, that would contradict what I've already said, right? Because that would mean that f of x is in fact in the ideal generated by x squared plus 1. So there must be a non-zero remainder, right? All right. And r of x not equal to 0. All right. And also, what do we know about the remainder? It has degree smaller than the divisor, right? So r of x is equal to ax plus b for some choice of a and b, right? And they can't both be 0, right? At least one of a and b is non-zero. All right, so let's rewrite that. What we have is ax plus b is equal to f of x minus q of x times x squared plus 1, right? And what can we say about that? Well, we're looking at is f of x is in b, right? And let's see here. Curses. Oh, I need to use the fact that, what am I assuming about B? This is contained within it, right? So the fact that x squared plus, the ideal generated by x squared plus 1 is inside B, that means that, q of x times x squared plus 1 is an element of B, which, by the way, is an element of x squared plus 1, the ideal generated by x squared plus 1, which, by the way, is a subset of B by assumption, right? So we have f of x is in B, and this is in B. Therefore, this whole difference is, again, in B. So this is the side comment there, okay? So then what? I say, moreover, a squared x squared minus b squared, right? That's equal to ax plus b times ax minus b, using difference as squares, right? Some algebra there. Now the point is, we're looking at a product of what? We're looking at a product of something in the ideal B, right? And something else, right? So we've just argued this is an element of B, right? This is an element of the whole ring, but by uber closure, the product of anything in the ideal with anything in the ring is again in the ideal, right? So this is, again, an element of B by the fact that B is assumed to be an ideal, right? But then what? So I said note that a squared times x squared plus 1 is an element of the ideal generated by x squared plus 1, which of course is a subset of B. So therefore a squared times x squared plus 1 is in B, right? And then what? Well, finishing blow here almost, 0 is not equal to a squared plus b squared. How do I know that? Remember I said at least one of them is non-zero? And that's also equal to a squared x squared plus a squared, right? Minus a squared x squared minus b squared. Check out the parentheses. So I've got an overall subtraction and addition of a squared x squared, and I've got a squared plus b squared overall there, yeah? So what we're looking at, though, is this is in B, and that is in B. So the difference of things in the ideal is again in the ideal, right? So therefore, a squared plus b squared is an element of the ideal. All right? And that's a non-zero constant. But since 1 over a squared plus b squared is an element of the ring, and 1 over a squared plus b squared times a squared plus b squared equals to 1, well, that's an element of the ideal. But one of the things we proved last time is that the reason we want sub RNG for the ideal and not sub ring for the ideal's definition is because if we use sub ring, including 1 in the sub ring automatically means from the ideal condition in Uber closure, we get the whole stupid ring. Well, here we go. We've got an ideal with 1 in it. Therefore, B is equal to R. And that's all we need to do, right? Because now we've shown that logically, either what? So either f of x is an element of x squared plus 1. Excuse me, either b is equal to x squared plus 1, which would be fine. That's the one possibility for b, for x squared plus 1 to be maximal. Or we've shown that the other possibility is that this b, this supposable intermediate ideal between x squared plus 1 and r of x, well, is actually all of r of x. So this proves the maximality of the ideal generated by x squared plus 1. So this is a kind of typical argument for proving maximality directly. Let's see here. Here's another example, which is like not quite the same. This is 4.3.5, a little bit easier. Here we have z2x. All right, so polynomials with z mod 2 coefficients has x squared plus 1, that principal ideal, not prime. All right. Why is that? Well, x plus 1 squared, right, is x squared plus 2x plus 1, right, which is equal to x squared plus 1. All right. And I say, so how do I say this? So of course, this is an element of the ideal generated by x squared plus 1, right? Yet, x plus 1 is not an element of the ideal generated by x squared plus 1. How do I know that that's, how do you, I claim that that's obvious. Is it obvious? Why is x plus 1 not an element? I've not written not yet. Sorry about that. Not an element. Why is this kind of obvious? Like, what would it mean? What would it mean for it to be an element? That would mean that you could find x plus 1 equals to what? X squared plus 1 times what? Times some polynomial, f of x, you know, for some f of x and z2. Can you do that? No, like, clearly not, right? Do you see why this proves that that's not a prime ideal? The proof is just this. You've got x plus 1 and x plus 1, right? They're elements of z2x, right? And their product, x plus 1 times x plus 1, is equal to x squared plus 1 by the above calculation, which of course is an element of the ideal generated by x squared plus 1. So here we have two elements of the ring whose product is in the ideal, right? Yet neither of the elements forming the product are in the ideal itself. Therefore, it's not prime, right? So here, this is like the A, this is like the B, this is like AB in A, so to speak, but it does not imply that A is an element of A or B is an element of A, right? Which proves that this is not a prime ideal from the definition, right? Okay. So, big theorem, really important theorem. Let R be commutative ring with unity, with identity, all right? Unity is just another word for identity, talking about the multiplicative unity, identity. And let A be an ideal of R, all right? Then the quotient ring, R by A, is an integral domain if and only if A is prime. Do you guys remember what integral domain meant? It was an integral domain. What property does an integral domain have? No what? No zero divisors, right? No zero divisors. Sorry, I'm impatient. Let's see here. Implies, forward implication. So suppose R mod A is an integral domain, right? Right? Let A comma B be elements of R and AB be an element of A, right? Now, suppose, let's see here, observe rather, AB plus A, what's that equal to? By definition of like multiplication in the factoring, this is equal to A plus big A, B plus big A, right?
And you got that from over there, right?
That's just the definition, but yeah. Right. Now, we're trying to do what? We're trying to prove that A is prime, right? So, what can you tell me about AB plus A?
If it's prime.
I mean, well, already, before, set aside the prime for a second here. On the basis of this assumption right here, what does that mean about AB plus A? What's that equal to?
Another thing in A.
That's another thing in A. In other words, that is, so like, that is the zero.
Yeah.
I mean, what I'm trying to say is we can set this equal to A again. All right, so in other words, this is the zero in R by A, right? That's 0 in R by A. But we're also having what? We have the product of two things in the factor ring is equal to 0. But the factor ring here we're assuming is an integral domain, right? Therefore, as R mod A is integral domain, A plus A is equal to A, or B plus A must be equal to A, right? Because either one of them or the other or both has to be 0, because the product of them is 0. But what does it mean for A plus A to be an A, to be equal to A? What does it mean for B plus A to be equal to A? So this is exactly the condition that A is an element of A, or B is an element of A. That's what it means for those cosets to be equal, for those sets to be equal. And that's exactly what we need to prove that A is prime, because we just proved that if the product of things in A, then either one of the factors or the other is in A again. Right? This is by definition showing A is prime. Therefore A prime. That's half the proof, right? we got to go the other way, right? Suppose A prime. Right? Consider A plus A times B plus A equal to A again, right? In other words, suppose you've got product of things equal to 0 in the factor ring. What do we need to show? We need to show that one or the other of those is 0. This, of course, implies, I mean, this is almost a biconditional proof, frankly, guys. AB plus A is equal to A, right? And I guess I'm missing something. The thing I'm missing is, it's kind of silly, but here it is. I should have said, let A and B be elements of the ring. There you go. Okay. Sorry, I forgot to say that. Now, A plus B is, so that, what does that mean? This means AB is an element of A, right? But that implies that A is an element of A, or B is an element of A, since A is prime, right? Which then says what? That says A plus A equals to A, or B plus A equals to A, which is what I need to verify that the factor ring is an integral domain, because the product of things 0 means one or the other of the things forming the product is 0. So this is a very nice theorem. So I'll go over here. Sorry, Caleb. So theorem 4.37. Again, same preamble as the previous theorem. It says that R mod A is a field. What's a field?
A field is defined by things that, like both the axioms of groups, like multiplicative and additive group.
Yeah, it's a ring, right? A commutative ring with identity, such that every non-zero element has a multiplicative inverse, right? So you could say it's a, well, anyway, you could say a lot of things, but this is the theorem. R mod A is a field if and only if A is maximal, right? So if this theorem's true, example 4.34, what's that say? That says that, you know, as a consequence, let me just write down, what does that say? That says that R of x mod x squared plus 1 is field. Since we proved that that's a maximal ideal, right? In fact, we recognize that field, if we studied it the previous class, as being isomorphic to the complex numbers. So a different way to look at this is, once we've proved theorem 4.37, we could run around the difficulty of example 4.34 by instead identifying that the quotient ring is isomorphic to a field, right? So if you have that the quotient ring is isomorphic to a field, that implies that the thing you're dividing by is maximal. Direct proof of maximality is kind of a pain. Recognizing something's a field that we already know up to isomorphism, well, that's a much easier project. So this theorem is very useful for avoiding the difficulty of example 4.34. Okay, so here we go. This proof's a little bit longer, but it's not much more difficult. So we'll do the forward implication. And actually, the forward implication of this is very reminiscent of the example 4.34. So we suppose our commutative ring with unity, we'll use 1 for the unity. All right? And an ideal, such that R mod A is field. All right? So consider an intermediate ideal. So we're going to suppose we've got A is a subset of B is a subset of R, right? And here B is an ideal. And we're going to assume, A is not equal to B, right? So just like the same logic as our first example today, our goal now is to show that B is equal to what? Because we want to show A is maximal. We want to show that B is equal to R, right? Same logic as the first example. We want to show B equals to R. All right, so if A is not equal to B, what does that mean? A is not equal to B. So there exists X, which is not an element of A, right? Let me say it in a more civil fashion. There exists X in an element of B, such that X is not an element of A, right? If they're not equal, there must be some point they differ on, right? And so that means that X plus A is not equal to A, right? So in other words, X plus A is a non-zero element in the field R by A. What does that mean? Remember, we're assuming this is a field. So there must be a multiplicative inverse, right? What does it mean to have a multiplicative inverse in this context? So there exists Y plus A in this, right? Such that X plus A times Y plus A equals to 1 plus A, because that's the multiplicative identity. But by the definition of the multiplication in the factor ring, this gives us xy plus A is equal to 1 plus A, right? What does that mean? That means that 1 minus xA, rather 1 minus xy, is an element of A, right? But I say, however, x is an element of B, right? That's true, right? Well, that was by assumption. And thus, xy is an element of B. Why do I get to say that? Y is an element in the ring, right? Remember, Uber closure for the ideal says anything in the ideal times the ring element is again in the ideal. So since x is in the ideal and y is in the ring, x times y has to be in the ideal again. This is definition of ideal. At some point, I should have said y is an element of the ring. I guess it's kind of implicit up here. This means that y is an element of R. That's kind of taken for granted if I write y plus A. Our notation means that y is an element of R, which is the representative of the coset y plus A. But anyway, so what then? Oh, so check it out. 1 minus xy, right, plus xy is equal to 1, which is an element of A, right? Well, I'm not A, rather. This is in B. This is in B. So 1 is an element of B, right? So just like our example 4.34, we've shown that the intermediate ideal contains 1. Consequently, B equals to R, therefore A maximal. If you really study the proof, like the logic of it is very much parallel to our first example. It's just our first example is mired in the technical details of the x squared plus 1 principal ideal. Conversely, how do we do this? Suppose A maximal, right? And suppose X is in the ring, but X is not an element of A, right? So I'm considering, thus, consider X plus A not equal to 0 in the factor ring, right? All right, I think this marker's over. It could have made it. Could have been it. Could have been.
Don't quit your day job.
No, I don't quit my day job. Yes, that's very true. Yeah, and I don't know how much there really is. I really don't know if there's any sponsors for like competitive marker throwing anyway. Like, I'm not sure.
Don't underestimate.
Now, I tell you what, I could repurpose my YouTube channel and start gaining, gathering interest in the sport. I could become the champion. Yes, the face. Well, let's not go with face. That's not a good choice for me. But, I could become the voice of competitive marker throwing. I'll show you guys. Okay, so actually, I'm going to. All right, fine. I've already got down here. Now, this is where it gets weird. It's like construct B equal to XR plus A such that R is in the ring and A is an element of A, all right? You can show this is an ideal. All right, so this is an ideal of R. Maybe I'll make that one of your homework exercises, and if I remember, I'll try to make this one of your homeworks in Mission 6, okay? That should be a pretty friendly homework, actually. I'm going to continue the proof up here because I don't like writing down there. Okay. So I'm claiming that's an ideal by your homework, right? And notice that if A is an element of A, right? Then check this out. A is equal to X times 0 plus A, so that's also an element of B, right? So what's that show? That shows that A, the ideal, is a subset of B, right? That shows that B, that means B is an ideal which supersedes A, right? And obviously it's a this is a subset of R, right? And what else can we say about it? So that means either A is equal to B or B, either A is equal to B or B is equal to R, right? Why is A not equal to B? I think that may be missing in my proof. oh, X is not an element of A, right? Notice X times 1 see, which this has to go? A is an A. Is 0 an A? 0 is an A, right? A is an ideal, so it's a sub R and G. So this, X times 1 plus 0 is equal to X, is an element of, B by construction, but X is not an element of A, right? Therefore, A is not equal to B because they differ on at least the element X, right? I think that's missing from my current proof. Bad. So, by maximality, what do we have? By maximality of A, we find B equals to R, right? Thus, 1 is an element of B, right? What's that mean? So there exists what? There exists R and R and A and A such that what? X times R plus A, right, is equal to 1. Right? But what does that say? This implies that, XR plus A is equal to 1 plus A, looking at the cosets, right? But of course, we can absorb A into that. So we've got XR plus A is equal to 1 plus A, which is to say that X plus A times R plus A is equal to 1 plus A, right? What's that say? What did we start with? We started with a non-zero element of the factor ring, right? So this implies that X plus A, the multiplicative inverse of it, is equal to R plus A in the factor ring. So we just showed that a non-zero, an arbitrary, right, a completely arbitrary non-zero element of the factor ring has a multiplicative inverse. That follows from maximality. That's what we've shown. All right, and I have some more details in the proof here. I'm like, okay, and you should observe that in fact, the factor ring is a commutative ring with identity, right? And it's a commutative ring with identity where every non-zero element has a multiplicative inverse. Therefore, R by A is a field. The factor ring is a field here. All right. So guys, next question then. So that completes the proof of theorem 4.37. So we have prime ideals, we have maximal ideals. What do you guys think the interplay between these two is? Are they the same? Are they different? What gives? Sure. So we had an ideal test, and so that kind of tells you shortly. Ideal A is a subset of a ring, where if we have A and B and A and B in the ideal and R in the ring, then you got A minus B is in the ideal, and, well, let me just write it all out. You have the difference of A and B is in the ideal, A times R, and R times A. They're all in A again. This was the this is the ideal test, which in some sense you could think of as the definition. It is a subset of the ring, which is closed, which is a sub-RNG, which means it's got 0 in it, it's closed under subtraction. But more than that, it satisfies these two conditions, which I refer to in honor of my colleague, Dr. Sprano at Liberty, as Uber closure. Uber closure, which says that when you multiply the ideal by things in the ring, doesn't matter if they're in the ideal or not, just things in the ring, they all get sucked into the ideal. Like ideal takes multiplication in the ring and it just sucks it in. That's what an ideal is. So, for example, in the integers, we saw that the ideals, an example of an ideal in the integers is just multiples of n. Like nz is an ideal in the integers. We have these principal ideals where we just take multiples of an element in the ring. That's an ideal, all right? But now we have the following result, right? Prime A says what? R by A integral domain, right? Maximal A, R by A field, right? So my question to you guys is there any interplay between these? Does one imply the other? Does the other imply the one?
Well, I thought prime meant max A.
Does prime imply maximal? Does maximal imply prime, which either or both of these true, why or why not? How about this? Are there 0 divisors in a field? They're not, right? So field implies that R mod A is integral domain, which implies A prime, right? So what we have is, in fact, maximal implies prime. That is true. Is the other true? Does prime imply maximal? It does not. Let me show you an example. All right, so here's an example of how that doesn't happen. So the example is this. So z polynomials with integer coefficients. All right. We can exhibit an ideal which is prime but not maximal. So he has the ideal generated by x is prime. I mean, think about it. If you had a product of two polynomials is in there, right? See that? If you had like a of x times b of x, let's say, is an element of this, what's that mean? That means that a of x, b of x is equal to like x times f of x for some polynomial with integer coefficients, right? So that means either a of x or b of x is a multiple of x, right? The x has to go into one or the other of them by just properties of polynomial. So that means either a of x is an element of this or b of x is an element, right? Which means that the ideal generated by x is a prime ideal. Because when we have a product when we have a product that's found in the ideal, either one or the other of the factors forming the product is in the ideal. It is a prime ideal. Is this maximal? Well, he points out, or rather I point out, that x is an ideal which is a subset of the ideal generated by 2 and x, which is itself a proper ideal of this. So it's easy to see that this is a subset of that because like this is linear combinations of multiples of 2 and x, so it certainly includes this. All right. This necessarily this does not have all of zx in it. For example, like 1 plus x is or just 1. There you go. 1 is not an element of 2x, right? Because 2x, this is things of the form like 2 times f of x plus x times g of x, such that f of x and g of x are in polynomials with integer coefficients. So if you look at that, there's no possible way you can recreate the constant polynomial 1. And yet 1 is in z of x. Therefore, this ideal is properly contained in the ring, and yet it is an ideal which supersedes the ideal generated by x. Therefore, this is a prime ideal which is not maximal. So they're not the same. Prime ideals are not automatically maximal. Although oftentimes they are, in our experience. Aha, so this brings us to lecture 24, I believe. If I haven't messed up my printing. Nope. So, so now we begin our discussion of ring homomorphism. And I think I'm going to actually start over here. What's a ring homomorphism?
A mapping which preserves the axes between 2 rings.
Yeah.
I guess it preserves the elements, those elements between.
No, you had it. It's a structure preserving map of rings, right? It preserves the axioms. But yeah, we can be more specific too, right? A ring homomorphism we'll call it phi from a ring R to a ring S, all right, is function. First of all, it's a function, all right, which preserves ring operation such that some terms and conditions apply. Number 1, phi of A plus B is, you guessed it, phi of A plus phi of B, all right? And 2, phi of AB is phi A, phi B. And 3, it has to map 1 to 1. So phi of the multiplicative identity in R maps to the multiplicative identity in S, right? If phi is bijection, it's a bijective ring homomorphism, then phi is a ring isomorphism. Right, and we write R isomorphic to S. Right. If R is equal to S, and you have a bijective, an isomorphism from the thing to itself, then it's actually called a automorphism. Well, I sure hope Audric's like, well, it's too late now. That ship has sailed. Yes, all right. The ship is erased. It was sent to the bottom of the ocean by a monster. So some examples. We could look at phi going from the integers to the modular, mod n by phi of x equals to the residue class mod n. So I had other notations for this. Of course, this is also x plus n z, right? That's example 1. And actually that example 1 plus, how about phi is a mapping from a ring to a ring mod an ideal, right? Then you could generalize the above example to the following. Phi of x is equal to x plus a. This is the so-called natural map, or the coset map. The coset map is a ring homomorphism. You can easily check that it satisfies these properties, right? Yeah. Example 2, which is actually my example 4.4.3. We're on page 137. Anyway, here it is. Phi, a mapping from the complex numbers to the complex numbers by phi of z equals to, well, I'm using star in the notes, so I'll do it here. A lot of times I use bars in math classes, but the complex conjugate, all right? Well, what are the properties of the complex conjugate? The conjugate of a sum is the sum of the conjugates. The conjugate of a product is the product of the conjugates. And what's the complex conjugate of the number 1? Well, it's 1 again, right? So check, check, check. We have that complex conjugation is a ring homomorphism of C. In fact, you can easily see that phi of z is what? Conjugate, right? What happens if you do the complex conjugate twice in a row? You're back where you started, don't you? So this, in fact, has phi composed with phi is just equal to the identity, right? In other words, complex conjugate's its own inverse, right? So it's certainly invertible, which means it's a bijection. So this is, in fact, an automorphism. So this is a complex conjugation. Gives automorphism of the complex numbers. And that automorphism has order 2, right? I asked you some kind of weird questions about finding how many automorphisms of order such and so forth Zn had, remember that unpleasantness? So this is kind of circling back to that a bit. Example, now this is a really powerful example that will be with us through certain abstract discussions, but there's also this thing called the evaluation map. Evaluation map. So here we have a ring, and then R of x polynomials with R coefficients, right? Let A be an element of the ring. Then phi, we'll do a phi sub A this time, a mapping from the polynomials to the ring is defined as such. Phi A of f of x is equal to f of A, with our usual meaning of evaluation, right? To be more explicit, what I'm saying here is phi A of like C0 plus C1x plus da-da-da-da plus Cnx to the n. Well, what's that equal to? Replace the x with the A, right? just to, this is the so-called evaluation map, and you can prove that this satisfies criteria 1, 2, and 3. It is a ring homomorphism. The natural ring homomorphism from the polynomials over the ring to the ring itself. How many different evaluation maps are there? Like I said, it depends on how big your ring is, doesn't it? But you can have a lot of them. Theorem 4.45. We have, I would just say, please read. I really don't want to write it out. I'll tell you what it says. It says, well, I'll hit some high points. How about that? Phi of nr is n times phi r, and phi of r to the power n is phi of r to the n. So these, in other words, the properties 1 and 2 extend inductively, right? This is the inductive extension of properties 1 and 2. And then we have other things like the image of a subring, the image of a sub-RNG is a sub-RNG. If you have a surjection and you have an ideal, then the image of the ideal is itself an ideal. The inverse image of an ideal is an ideal. If R is commutative, then the image of R is commutative. And phi is an isomorphism if and only if phi is surjective and has kernel 0. And finally, phi is a ring isomorphism. Then its inverse map is a ring isomorphism. So I probably will assign you the proof of one of these, or two, maybe in your admission 6. These are not difficult to prove, and I think they're pretty good homework exercises for you guys at this point. Let's actually prove something here. Theorem 4.46. Here we have phi r to s ring homomorphism. All right. Then the kernel of phi is an ideal. Now, let me remind you what kernel phi is. So the kernel is defined additively, I believe. So kernel of phi is equal to r in the domain for phi, which is in this case is r, such that phi of r is equal to 0. So the kernel is the set of all things that it sends to 0, right? In other words, you could say that the kernel is the inverse image of 0.
Is this just this definition? I seem to remember a different definition.
Are you thinking about groups?
Yeah.
So in groups, it would be the set of things which are mapped to the identity. Yeah. But here we talk about additive kernel. So the additive kernel is most interesting to think about because the group is abelian and therefore normal, and so you can, all of our factor ring constructions are with respect to the additive cosets, so like this is additive kernel. All right, you could think about the multiplicative kernel, I suppose. Like, definitely, what's the inverse image of 1? Well, it definitely contains 1. Does it contain other things? Depends on the map. But anyway, here. So we want to prove that the kernel is an ideal. What should we do?